Thanks everyone for joining our next webinar. So we do again the second time our NanoFrazor technology introduction. So you might have seen we have a whole webinar series about this technology. And today I do our introduction. So I will talk about, briefly explain the main aspects of a technology and show a few key examples that illustrate the capabilities of this technology. But before I will start with an introduction on where we come from and who is using the machines today and why, a little bit on that. And in the end, I also show a little bit about the actual products we are selling. Okay, so I hope everyone who is joining here will learn a lot. And now I get started with a little introduction. Okay, so Heidelberg Instruments is actually mainly known for laser writer direct write lithography systems. And we are selling from desktop small systems to very large, high speed mask writers and direct wafer exposure systems. And there's a remarkable number of around 1,000 systems out there. We are around 250 people worldwide. And since 2 years, we have also a system in offer which goes to lower dimensions than limited usually by light exposure. And that's, of course, the NanoFrazor system. So this technology originates from IBM Research. It has a long history. I will tell you on the next slide. And yeah, we joined Heidelberg Instruments in 2018. We are around up to 20 people in Zurich, working mainly on development and improving this still young technology. And that will be the topic of today, how this technology works. So the NanoFrazor has a long history. So using heated tips for nanofabrication has been already demonstrated here in 1992 at IBM in Almaden. And then I think as the biggest visibility it created during the so-called IBM Millipede project, which ran over a long time with a lot of effort in Zurich at IBM Research Zurich. And during that time, they actually integrated thousands of these heatable tips on a CMOS chip to write, read, and erase data with at that time actually data storage density world records. But it was not economically competitive to flash, which became too fast, too good, and too cheap. So this was stopped. But a few people continued at IBM Research, and in my opinion, the breakthrough was then the discovery of suitable resist materials, which allowed us to write with high speed and high resolution. And that, in the end, me and Philip Hall, we decided to leave IBM and make a company out of this technology to make this technology available to everyone. And since then, we are still collaborating closely with IBM and others. We improved the technology a lot. We launched the first systems in 2014 and still improving these systems with software updates and so on. So it's still a lot of development work ongoing for getting this technology really to have a high impact. And 2 years ago, as mentioned, we merged with Heidelberg Instruments because we see a lot of synergies with their expertise also in industry and their high-speed laser writers on the microscale and our technology making nanostructures. So today there are a little bit more than 25 systems distributed all over the world here. You see a few example customers here from Europe, America, Asia, or Australia. And actually they are quite diverse customers. So on the one hand, we have, I would say, clean room, multi-user clean room facilities. And on the other hand, we have you can use the NanoFrazor lithography system also outside of a clean room. I mean, it can be convenient in a clean room if you have all the other instruments closed, but you can do also all the advanced nanoprocessing and fabrication outside of a clean room. Some people put it also inside a glove box, as you see here. And also we have a few industrial and military customers. So it's moving also in various directions. And what people use the NanoFrazor for is also very diverse. I put this cloud here with a few buzzwords or keywords on topics people using the NanoFrazor for. So in general, you can use a NanoFrazor wherever you need artificially made nanostructures on a surface. And we divide it in our customers or application range. You could divide in two fields. One is we call standard devices. So that are devices you could also do with normal e-beam lithography. But not everyone has access to an expensive e-beam lithography system, or they are occupied a lot, or actually for some applications also NanoFrazor is actually much more convenient and easy to use. So that's what we call the standard devices. But I would say at the moment, the majority of our customers, they acquired and use the NanoFrazor because they are working on something new, which is not possible by conventional nanofabrication techniques. And that can be related to making structures that require very advanced precision, be it on the 3D scale, or you have very complicated overlay things, or complex high-resolution features, which are difficult to do with other techniques. And on the other side, a lot of our customers also work with new materials or sensitive materials, which might be damaged or not working at all if you try to fabricate or shape them using conventional nanolithography methods. Okay, so I guess most of you know the key concept is using this heated tip for nano patterning. And the question is, why is such a heated tip interesting for patterning at all? And I mean, if you think about it, in principle, you can heat up any material, right? You just bring it in contact with this nanoscale heated tip and you heat it up, and all materials at some temperature at least react to heat. There have been many publications on how you use the heated tip, for example, to modify or convert materials physically by phase changes or make chemical changes. Also, people have shown that you can actually coat the tip and deposit material from a coated tip or from the gas phase. There have been a few very little papers here. I want to refer mainly to this review paper we recently wrote with EPFL together to summarize and compare these different approaches as how you can use a heated tip to write nano patterns in various ways. And this is, this whole conversion thing is super interesting, but the majority of people, I would say more than 90% of our users are using what we call the standard approach for NanoFrazor lithography, and that's also what I'm talking about today. That is using the heated tip just to remove special thermally responsive resist from the surface. So wherever you touch the surface, this resist is immediately gone. And the big advantage of this approach is it's very fast. So it is happening on the microsecond time scale here. You will see you can do high resolution and you can write very accurate features, but mainly it's very reliable. You have a wide, let's say, temperature window where you can apply this, and it's very simple to do and reliable. And also a tip, because you don't need a mechanical force to write these structures, the tip lasts very long in comparison to other approaches. This approach here also triggered the name Fraser, NanoFrazor. That comes from the German name Fräse, which is a milling tool, and razor blade, for meaning that it's very sharp. Also very important, if you use this approach, you do the lithography just in this thermally responsive resist, but then you have a whole slew of recipes available. So to convert it in all kinds of materials by different means. So you can do high quality material transfer by lift-off, etching, molding, plating, and so on. That's very important because in the end, you want to fabricate real nano devices. And we have a whole recipe book covering all these processes here available for our customers. Okay, so but now I come a little bit more details about the technology. So really the core part of our technology are these thermal cantilevers. They are all made of silicon, and they have this tiny, very sharp tip sitting here on top of a 2-micron sized micro heater. And this heater we can control very accurately between room temperature and around 1100 degrees to heat up the tip and then do the writing, right? Also very important, not like usual AFM cantilevers, they have an integrated electrostatic actuation to move the cantilever electrostatically very fast and accurately up and down. And also very important to note, we have an integrated sensor here, sitting here, there's a point here, doing the AFM imaging and also other calibrations. So yeah, but then in the end for writing, we use this nanoscale tip, fly over the surface, remove the material, and then you have your pattern and your resist. The Explorer machine has also a laser integrated, so you can do the same approach also with a focused 405 nanometer laser, just to speed up things if you do micrometer structures. But what I want to point out here, what is very important for the NanoFrazor principle is that we combine writing with reading. So we have this in situ a high-speed AFM capability using the cold tip to do inspection, metrology, overlay, and stitching. I talk about that later, in situ. And that's very important because that brings combining this writing and reading, that's where the true power lays of the NanoFrazor technology. And maybe just to mention, we have this integrated distance sensor here in the cantilever, and we use it not only for AFM imaging, but also to do a lot of corrections and calibrations. But I mean, the user doesn't need to know about all these details here, what's happening in the background of the machine. Okay, so having this in situ capability to measure topography, that allows us a concept we call closed loop lithography. So we do patterning and imaging at the same time. And it's in a simplified and slow motion way. It's illustrated here in this video. So the cantilever with a hot tip moving in one direction is removing a resist according to your design. And then if you switch it off, it takes actually just a few microseconds, and the tip is back at room temperature, and you use it as an AFM, and you measure what you have just written. And then the software compares if you actually did what you wanted to do from your design, and even slightest deviations of a nanometer then can be corrected and adapted. And that's a very powerful scheme. Actually, we have a separate webinar just describing the details of this approach. Here it's simplified, but in the end, also the user here, you don't need to know in detail how this is working. The nice thing, it makes the whole thing very reliable and easy to do, because that's in a standard mode always running like this, so that we're always checking if the machine is doing the correct thing. And this approach, this closed loop approach, that allows you then to do what we call 3D or grayscale patterning, so 2.5D, we could say, very accurate removal of material. So you achieve here actually a standard deviation of less than 1 nanometer. So you can do steps here, like here, this 1.5 nanometer steps, or continuous structures with very high accuracy. And that's interesting, not just because it's cool and accurate. Actually, indeed, it opens up completely new opportunities for devices which have not been possible to make before. And here are a few examples which have been published in recent years. We just heard this week Nolan talking in a webinar about new optical Fourier surfaces. This will be also published in Nature soon. Super interesting approach of combining sinusoidal structures very accurately written with a NanoFrazor to have interesting diffractive properties of your surfaces, and a very cool approach. He will actually repeat his webinar also in one of our morning sessions, probably in June or July. So you stay tuned here. I mean, it's clear that optical application anyways is interesting because light, you could say, fields every nanometer of your surface. So there are different examples here also going towards kind of quantum devices. But interesting, there's also some examples now going towards bio applications with these kind of surfaces for stem cell differentiation. And also, we will hear in a separate webinar, this is what IBM is doing now, is nanofluidics. So they write 3D structures into a nanofluidic channel. And in this case here, they create a potential landscape so that they can have nanoparticles moving in completely opposite directions triggered by Brownian motion. That was published in Science 2 years ago. Super exciting. And they will talk soon about what they are doing now with this technique. So they integrate it into microfluidics and so on. So stay tuned if you are interested here. There will be a separate webinar on this. Okay, so that's the high accuracy in 3D, but of course everyone is usually interested also on how accurate you can get in 2D. So what's your actual resolution? And here, in quick summary is, of course, we are limited by how sharp our tip is. Our tips are usually sharp. And what we specify for our machines is 25 nanometer half pitch. That doesn't mean you can go below. People have been going below even 10 nanometer half pitch. But 25 nanometer, that's just what we know that we can do. Just actually on the same day we do the installation, you can do 25 nanometer half pitch. Everything below it becomes a little bit more tricky sometimes because also if you, for example, write deeper or the, it's a polymer structure, an organic material, and small structures, they also tend to then collapse or get destroyed. So it's a little bit more complicated to go to below 10 nanometers, I would say. That's a general thing. You can do, probably it's easy to do some high resolution features very shallow in resist, but in the end, if you want to make a nano device out of it, in our case, you should be at least something like 3-4 nanometer deep so that you can transfer. And that's actually one of an important thing we also put in a lot of development work is how to get these shallow high resolution features you have in your resist, which is the case also for other lithography methods. Usually your high resolution features in organic resist are rather shallow, not too high aspect ratio. How can you amplify them and get them into all kinds of other materials? And that's an important topic. We have also a separate webinar on how do we do that in detail. In short, we use a transfer layer stack and etch it. And then you can see you can do very nice high aspect ratio features, for example, in silicon, or here that's etched into gold. And we did a lot of work here with IBM, also with IMEC, as you see here. So that's a very important thing. Also, you can use a similar approach for making lift-off, high resolution lift-off here. You see a few examples here. You can do very high resolution features by lift-off also, but you require a reactive ion etching step before to create this undercut, which is required for the lift-off process. Also, we will talk about that in a later webinar in detail. I would say even more used process, or a very standard process of our customers, is what we call the bilayer lift-off. So here you write with your tip into the PPA or the resist layer on top, and then you have another resist layer underneath. You create your undercut here in a development step, evaporate your metal, and do a lift-off. And you can do also high resolution features, but in density you are limited. And we have various recipes of these resists depending on the substrate and the actual application. And we will talk about this process also in a separate webinar, because it's a very important process to understand and to know what to do for which application. Okay, then for real device fabrication, it's not only about high resolution features or dense features, it's also very often it's required to place the pattern on a very precise location on your substrate relative to an existing structure. And usually people use markers, artificially make markers somewhere on the structure which they detect and then have to move from the marker to the region of interest. We do that for high resolution or high accurate overlay. We do it differently. You can actually image the structure which is buried under resist. You can detect it, and then you draw on your AFM image. You can draw the structures you want to write, like these side gates here on these nanowires. And this approach is super sensitive. For me, it's still amazing. You can actually see one single layer MOS2 flake under 200 nanometer of resist. You can nicely detect, as you see here, and then you write. You can shape in a way the flake on top in the resist and then etch it, like in this case here. And also here about this, how this process works in detail, we have a separate webinar on this. Okay, with this overlay, you can make, for example, these top gates here on this nanowire, indium arsenide nanowire transistor. But I show this example here because that was actually our first example where we realized, hey, actually, it's a real advantage that we don't use a charged particle beam for making lithography. Because here at IBM, they used to do these devices with e-beam lithography only. And they had always issues because if you write here on top and you have a gate, insulating gate oxide around your nanowire, you have some trapped charges and your sensitive nanowire transistor doesn't switch properly at 0 volts and behaves a little bit weird. And here the first device we made was outperforming all the devices they made before. And that was for us really a point where we said, hey, actually, that's a really big advantage for many sensitive devices. And indeed, this is now one of the key selling points, I would say, for our technique. And we call this non-invasive lithography. So it's not only about charging an insulating layer, which is in general can be an issue with non-conducting surfaces or layers for e-beam lithography, for example. It's also that I mean, in other like e-beam lithography, most of your energy is deposited actually in your substrate and can create, depending on your substrate, can create some damages, like you can get some vacancy, lattice defects, or you create new bonds between your resist, for example, and your top material. So you can have some damages. For many applications, that's not a problem, but there are some things where this is an issue. And we actually don't damage the substrate below. I mean, we have people who are afraid that with our hot tip, you would actually damage a sensitive material here. But also in a separate webinar, we will cover this whole topic of how hot it actually gets here, what's the temperature here, and what's the temperature here on where your sensitive material might be. And you will see this is not heating up, maybe not even maybe to 10 degrees or so. That's not heating up here. It's only heating up at resist on top. Okay, and that approach enabled, for example, also this nice paper published last year. So here they compared MOS2 transistors made with NanoFrazor and made with e-beam with PMMA resist. And here you see actually the residues and the roughness they have here with e-beam, and that creates a Schottky barrier, and which, I mean, if you have a high contact resistance of your super nice material, you can't make a proper or like a real device out of it, because then the contact resistance dominates the performance of your device. And here they could show they could really make omic contacts on these 2D materials in this paper. And also there was there will be probably also repetition of just about this topic by Ray from NYU. Okay, so maybe I go one back. So, I mean, you see these devices here. This part you write with the NanoFrazor super fast, but here to make these contact pads for wire bonding, which are here 100 microns, that takes maybe 10 minutes to write one contact pad. And if you have a larger array of this is kind of a dominating writing time, which is taking time. So the question comes up, what's the limitation of our patterning speed? And to make it short, in the end, what we are limited is mechanics. We have to move this tip accurately and fast by means of piezo motors and this electrostatic actuation of the cantilever. And that's in the end limiting our speed. And as a rule of thumb, you can remember these numbers. So we scan typically with a millimeter per second. And in the effect, you can cover, like if you pattern everywhere with around 50 nanometer resolution, you cover 1,000 square micron per minute. But the key thing is you get also an AFM image while you do the patterning. So you have later on one huge AFM image of all your pattern. That's a big advantage. And this speed, if you compare it with e-beam lithography, for example, that's similar to very high resolution e-beam, where you have to use a very resist-like HSQ, which needs a high dose, and you have to work with low beam currents to achieve this ultimate resolution, and then you're on the similar, let's say, low speed. And because we have this issue of not being super fast, we also introduced now, just last year, integrated laser writer also, because for applications like here, where you have these contact pads, now in this machine, you will write all these bigger wires and the contact pads, you will write directly with a laser. It's in the same resist layer and the same tool. You will remove the resist, and you can also image it if you want with a tip, and you align then your nano patterns very accurately to these micro features, and that saves you a lot of time. So this is then 100 times faster roughly than writing just with a tip. So that's really nice for rapid prototyping. And you can do also rather high resolution or sub-micron with a tip, but we target a micron resolution here with a laser. And there will be also a webinar talking about the details, how this direct laser sublimation process, it's a little unconventional how that works. Actually, the first time this will be presented this afternoon already. Okay, but the laser doesn't help you much if you have structures like this where you need high resolution features all over. So this is a 500 micron sized reflective hologram consisting of a lot of pixels. And here we actually also had to stitch fields together. So our writing field is 50 micron. And for the stitching, we actually use also our in situ alignment capability. So we measure with a cold tip before we write the next field to align the fields with very low stitching error. But in general, again, this then takes rather long. So this took around 10 hours to write and image this whole pattern here. So in order to increase throughput further, what we are working on right now, and which we plan to bring out as a test version by the end of the year already. So we are actually looking for suitable beta site customers right now, is a linear array. So we go again for parallelization. So we will use many tips in parallel in the future, and you see how this looks like. So yeah, I mean, it's clear now, if you would actuate or operate each cantilever or individually, you could increase the speed by up to a factor of 10. And then we envision also to use many of these scan heads in one machine, but this is really then future, but not something we will have next year. Okay, then, but I mean, even if you would use, let's say, 1,000 of tips, we won't be a high throughput technology. So for really making manufacturing of devices or consumer devices where you want to cover the whole area, this won't be the approach. Where we see our technology is for mastering, so making these very accurate 3D masters, which we then can replicate by nano-imprint or injection molding. So we have actually, together with partners, we showed various approaches. So you could, for example, here, this was etched into silicon first and then replicated with almost stamped and clear process by microsys technologies. But interestingly, you can also use the PPA thermally responsive resist directly to make like a transparent UV soft master, like in the SmartNil process from EVG or in the Skill process. So that's interesting. And even maybe more interesting is you can use this PPA master, like this 3D structure, and you can do directly on top, you can make a plate nickel. And then you have an inverted 3D structure in nickel. And in this case, this was put into this injection molding machines and then replicated with very high speed. So that's also a very interesting approach. So this, in my opinion, would be the things how you would use the NanoFrazor for mastering and then for high throughput manufacturing. So at the moment, we are selling two machines. One is the Scholar, the other one is the Explore machine. The Scholar is smaller, so it fits also into a glove box. You usually work with smaller sample sizes. And the Explore system has this integrated laser writer module. Also, this will be compatible with a multi-tip add-on, and it allows up to 4-inch wafers to write on 4-inch wafers. So these are the main differences. We will have also a separate webinar talking about more details of the machines, about the software, about the hardware inside. So if you're interested in more details about this, please you're welcome to join our product and sales webinars, where we also actually talk about how to raise funding for such machines, which is, by the way, rather easy because it's still very unique and it's you have a high probability to have a successful current application, because it's still very new, this whole technology. Also, as an outlook, we offer a NanoFrazor Professional, so that will be with a bigger stage for larger wafers. But in the end, it would be, I mean, it's not, no one has such a machine yet, no customer. So what we want to bring out here, we do customized machines also. In particular, we're interested to work with industry partners here to get this technology towards manufacturing together with industry partners. Okay, I mentioned here we have these webinars talking more about the details, about the different specifications you have. So again, you're welcome to join these webinars. Okay, I come to my end. I want to summarize the key take-home messages for you. So the standard NanoFrazor technology, so removing resist, that allows, first of all, the key thing is you can then immediately inspect what you have removed here, which is a really, in my opinion, absolutely crucial to be reliable. You go down to 10 nanometer resolution with a tip and with a laser to actually sub-micron resolution. And maybe important to mention, so it's not a high throughput technology, but we are around 1,000 times faster than usual AFM lithography, like anodic oxidation or dip-pen lithography, just because we are not limited by the interaction time. So here the heating is done in microseconds and the removal, while for other AFM lithography, you have to stay in microseconds, milliseconds. And yeah, very important to note now, for rapid prototyping, this 100x increase of speed with a laser is very advantageous. Also, I want to point out again, we have a lot of recipes for standard transfer processes like lift-off and etching and so on. We will talk about that in separate webinars, but also we support our customers with all these processes also, because in the end, what we want is that our customers quickly manage to make advanced nano devices. And sometimes the difficulty is not the lithography, it's more how to do the next steps. And here we support our customers as well. Also to mention again, this in situ imaging capability allows this markerless overlay and stitching I mentioned before, and very unique, this 3D lithography, which is very interesting for a few optical or nanofluidic biological applications with this 1 nanometer accuracy. So we see the applications of a NanoFrazor mainly in rapid prototyping, so fast fabrication of nano devices, small nano devices, small area nano devices, and for the fabrication of templates like this Nanoimprint or injection molding. And the unique opportunities we see, first of all, in this 3D grayscale patterning. Then I talked about this non-invasive lithography, that you can work with materials that otherwise might be damaged during lithography. And also interestingly for scientists is that you can use this heated tip to convert materials directly. I didn't talk about that much today, but actually next week there's a talk about a very exciting example by Eduardo Albisetti. He will talk about how he used the heated tip to make magnonic structures directly. That's very exciting. And in my opinion, there are endless possibilities. This has just started, so you can explore many things in material science and convert materials here. So that's a whole different aspect I didn't touch today. All right, and with this, I thank you for your attention.